welcome to all of our participants, and a special thanks to our panelists. This is the SF Big Analytics Meetup, and we are here to have a great talk for you today. I'd want to give a great big thank you to AI Camp and Bill from AI Camp for really organizing this webinar and making sure that it can happen and we can bring you this awesome talk today. Very quickly about this meetup, if you want to see the recording for this meetup and any other meetup, check our YouTube channel. We post everything there, and of course you'll find every video that we've done, from infrastructure, data processing, machine learning algorithms, the whole spectrum of SF Big Analytics. Today we have a fantastic talk. We have the co-founders of Data Mechanics here to speak with us. Getting started with Apache Spark on Kubernetes. This is a topic that's near and dear to my heart, and I think all of you participants will be very excited to hear. We have JY Stefan and Julien Demoser, who will give our talk today. So just quickly, I'll talk to the agenda and then hand it off. We're going to have, it's going to be one long talk today, so we get to do a deep dive, and we're so excited about that. We'll have some Q&A about 105, and then we'll close. So anybody has questions, please use the Q&A feature within the Zoom. Write them there, and then at the end, we'll make sure that the questions get addressed. There should be plenty of time. Okay, so JY and Julien, please take it away.
Hey, yeah, sounds great. Thank you so much. Hello, everyone, and thank you for having us. So yeah, today's our session is on getting started with Spark on Kubernetes. Just note that we'll be giving a talk. Great, June, you're presenting. We'll be giving a talk on the same topic next week at the Data plus AI Summit Europe, the conference organized by Databricks. But it's not going to be exactly the same content. We'll be going a bit deeper today because we have 45 minutes. So yeah, we look forward to that. Next slide, please. So just a quick introduction. I'm JY. I used to work at Databricks before starting Data Mechanics. So I was a software engineer. I led their Spark infrastructure team. So I have more experience with Spark really as an infrastructure provider. And then Julien, who will talk later, he's our CTO, and he worked with Spark as a data scientist and a data engineer. So he's more really experienced with Spark on the application side. Before I dive into the topic, I just have two slides where I give a bit of background on data mechanics. I will go over them quickly because one of the rules of this meetup is to avoid marketing, and we will respect that. But I just want the audience to understand why we're giving a talk on Spark on Kubernetes, how come we're familiar. So data mechanics is a Spark platform deployed on a Kubernetes cluster inside our customer's account. We try to make Spark on Kubernetes really easy to use, really cost effective, and also flexible. I won't go through the feature list, but it all comes down to simple intuitive UI, some integrations with Jupyter, with Airflow, and some dynamic optimizations to make Spark pipelines more fast, more stable, more cost efficient. Next slide, please. So now you'll see our architecture. So we are deployed on a Kubernetes cluster inside our customer's cloud account. So if the customer is on Amazon, we use AWS EKS. If the customer is on GCP, we use JKE. If they're on Azure, we use AKS. And on this cluster, there is one service running all the time. We call it the gateway, and the gateway is the entry point to launch Spark applications, either notebooks like Jupyter notebooks, or programmatic applications through our REST API. And so you could connect Airflow or other scheduler. Once the request hits the gateway, we're going to actually launch the Spark apps, configure them, scale them, and give you access to a monitoring UI. Okay, so that's it for the background on us. Next slide. Here's the agenda for how we're going to spend the next 45 minutes. So first, just a high-level introduction to Spark on Kubernetes. What is it? How does it compare to alternative like running Spark on Yarn? Second, we're going to get into the meat of how to get started with Spark on Kubernetes. And later, part 3, Julien will do like an end-to-end demo of what the dev workflow is. And last, I will talk a bit about the future works that are being planned or being worked on right now for Spark on Kubernetes. Great. So next slide or next two slides, the core concepts of Kubernetes. Next slide. Um, okay, before I jump into Kubernetes, Spark, I think most of you are familiar, but it's a distributed analytics engine for big data and machine learning. What made it popular? It's fast. It's relatively easy to write Spark applications thanks to its APIs in Python, in Scala, in SQL, and other. And it's versatile. So the most common use case is like ETL or data engineering. Then it's also used as a data science tool for interactive data exploration, analytics, or even machine learning. And finally, there's also streaming. Next slide. So one thing that Spark doesn't do is manage the infrastructure. So when what Spark does is take your code, split it into tasks, and then distribute it to Spark executors. But the infrastructure backing the executor is not managed itself. So it needs a cluster manager for that. Kubernetes is a new cluster manager for Spark. Before Kubernetes, you had standalone, which is built in with Spark and is basic but limited in feature. You had Mesos, which is an open source project, which was very popular once, but less so recently. And then you have Hadoop Yarn, which is by far the most common option for running Spark, until recently at least. And Kubernetes is the new kid in the block. It's natively supported since Spark version 2.3. So in the next slide, I'll show you what does this native support mean. So it means that the Spark, when you run a Spark application on Kubernetes and the Spark driver are going to be natively, directly talking to each other. So when you submit your application, you actually submit it to the Kubernetes master, which will understand your request and start a driver pod. So the pod is basically, to make it simple, a container in Kubernetes language. And then this Kubernetes master and the Spark driver are going to be talking with each other to request executor pods and start them, and then schedule tasks on them. And in fact, this exchange between the Spark driver and the Kubernetes can also happen dynamically during the lifetime of an application if you enable dynamic allocation. So next slide. Here I've talked about Spark Submit, but there are actually two main ways of submitting applications to Kubernetes. Spark Submit is really the vanilla way from the Spark main open source repo, and it works. I would say that app management is a bit more manual. The main alternative is to use the Spark on Kubernetes operator. And this is an open source project developed by Google, now open source, that works on any platform. And with this operator, a Spark application becomes a Kubernetes object that you can configure in Kubernetes style YAML, that you can read logs from, that you can kill, restart, schedule. So honestly, I would recommend using Spark on Kubernetes operator. It's really nice. I would say one downside is it is a long-running system pod. So the operator itself is basically a pod running on Kubernetes, which will be watching events from the Kubernetes master. In the next slide, we'll see how it looks like in practice. So on the left side, Spark Submit, basically just traditional Spark Submit, except that in the master URL, you have this Kubernetes, which indicates it's going to be running on Kubernetes. But then if you want to describe your application, you have to deal in with pods directly. So it's a bit manual. And then on the right side, you can see that if you want to start an application with the Spark on Kubernetes operator, you just treat it as a regular Kubernetes object. And so it becomes that you can describe, restart, schedule, and so on. Next slide, please. Great. So yeah, we just saw the core concept. So now let's talk a bit about the differences between running Spark on Kubernetes versus Yarn, which is the main alternative. So yeah, next slide. Regarding dependency management first, on Yarn, Um, Most of the time, you have a global Spark version for your Yarn cluster, and you also have some shared dependencies. On the Kubernetes side, obviously, you're running Docker containers. Your Spark distribution and all your dependencies are going to be packaged in a Docker container. So that means different person running on the same Kubernetes cluster can have their own Spark version, their own Python version, and dependencies. Similarly, Docker lets you control your environment in a more granular way. So instead of using init scripts, which take which execute at runtime, it can be flaky and take some time to run. You just build your Docker image for once, and then you're going to be able to run this Docker image locally or in the data mechanics on the Kubernetes cluster without any environment change. So in that regard, Spark on Kubernetes kind of gives you the best of both worlds. Isolation between concurrent apps as if they were running on their own tiny cluster, but also the cost efficiency of having a shared infrastructure. Next slide. Yeah, one note about startup time. Typically on Kubernetes, application starts really quickly. So if a node is available, so if there is room for your pod to be scheduled, it typically starts in a few seconds. If you need to get a new node from the cloud provider, then the Kubernetes cluster needs to scale up. And typically this adds 1 or 2 minutes. But overall, yeah, Kubernetes has a lower overhead than Yarn, and so applications start up quickly. Next slide. So another difference, obviously, is the ecosystem, and probably that's one of the main reason why companies choose to adopt Spark on Kubernetes is because they're already using Kubernetes for other parts of their stack, and they like the fact that it's a cloud provider abstraction, so it's available on the 3 big cloud provider, and they can plug in other tools like around security, networking, logging, and so on. In the next slide, one quick note about performance. So I was saying Kubernetes can allow some cost reductions because you're going to be sharing an infrastructure. But if we look at one specific app at a time, the performance is kind of similar, which is good news, right? There are not so many differences. This is more up to Spark. So we ran some benchmarks with the TPCDS, and we took the similar hardware running on Yarn and running on Kubernetes, and there weren't any significant differences. Okay, next slide. So we've seen kind of, okay, the pros and cons, I guess, of running on Kubernetes and Yarn. I guess I didn't say too much about the con side. I will, okay, to be fair, a couple of cons. First, it's still, it's only been out since 2018. It's getting more and more stable and production ready. In the last part about the future works of Spark on Kubernetes, I'll be talking a bit about that. And then I guess a second con is if you're not using Kubernetes, well then setting up the Kubernetes cluster in the first place might be a lot of work. And so we're going to look at that in the next section. So what is the setup checklist to get started? We won't be able to cover all the points, but we will cover a fair amount of them. So obviously the basic stuff is you have to create the Kubernetes cluster with proper networking, data access, node pools. You probably want to install the Spark operator, which makes Spark application management more easy, and the cluster autoscaler, which will let the Kubernetes cluster automatically add new nodes or remove them based on load. On the monitoring side, we'll cover this in the next few slides, but you probably want to have a way to host the Spark history server, so to have access to the Spark UI and also collect some metrics. And then we'll also be going to be covering some critical optimizations to make your application faster, including shuffle optimizations, and also to configure your Spark applications the right way. And also, if you want to reduce your costs, we'll be covering how to configure Kubernetes to use spot nodes. Without further ado, I think I'll leave the floor to Julian, who will cover these points more in depth.
Thanks, JY, and hi, everyone. I'll now talk about a few tips to improve performance of Spark on Kubernetes. So first, let's talk about pod sizing. Let's assume that you have a cluster with 4 core instances. The natural thing to do is to request 4 cores per executor. But if you do so, you'll never receive an executor. They will be stuck in a pending state. The reason is that you need to take into account the share of resources that is reserved by the system and by Kube. The full node capacity for cores is not available to pods. What is available is called node allocatable. It's usually around 95% of node capacity. It depends on the size of your node and the Kubernetes settings by the cloud provider. And even that is actually not available to the executor pods. There are usually some daemon sets running like fluentd, and so eventually, in my example, you only have about 90% of the node that is available to your Spark executor pods. So the correct configuration here is to set Spark executor cores to 4, so that Spark runs 4 tasks in parallel on a given node, and set Spark Kubernetes executor request cores to 3.6 CPUs, so that the pod is actually scheduled and created. And note that a similar thing must be done with memory, but we won't go into too much detail here. Then another thing about performance in the context of Spark is shuffle. So there's quite a few things to be said here. So first, if you have a shuffle-bound workload, and if you just run it by default, you'll realize that the performance of Spark on Kube is worse than Yarn. The reason is that Spark uses local files during the shuffle phases, which causes lots of disk I/O. And depending on the nature of your disk I/O can be more or less fast. A good thing, though, is that starting with Spark 3.0, Spark uses by default the file system of the underlying node, and not the Docker file system, which is incredibly slow. But you can actually do much better and be on par with Yarn by mounting some local SSDs into your machine. This yields a tremendous improvement for IO-bound workloads. On the right, you can see how to configure it. We're mounting a directory from the underlying node file system into the Docker container with the Kubernetes host path. If for your machine local SSDs are not available, you can just increase the size of your disks. The reason is that larger disks have a larger throughput. And on the right, you can see some numbers about this. This is the speed up of using a 500 gig disk instead of a 100 gig disk for the queries of the TPCDS benchmark. On the x-axis, you have the amount of shuffle data for every query. And so the queries on the right are the shuffle bound ones. You can see a 5, even 6x improvement for those queries. And so as JY said, if you want to learn a bit more about all this, we wrote a blog post on the topic of performance with Spark on Kube a few months ago. Okay, beyond performance, it's also important to reduce cost as much as possible. And we're going to see now a few tips to do so. The first tip is enabling support for multiple node pools. This is important because the different pods on your cluster have different needs. The system pods, if you will, like the Spark operator pod, must run on a node pool with small on-demand nodes. Small to reduce costs, as the Spark operator pod must always be up, and on-demand to guarantee availability. The Spark driver pods, on the other hand, must run on on-demand nodes of a medium size. This node pool should autoscale from 0, so that you're not paying for resources when no Spark application is running on the cluster. It's important to use on-demand nodes here because a spot kill on a driver would cause the application to fail. And finally, the Spark executor pods should run on larger spot nodes since a Spark application can recover from a lost executor. So let's see now how to set this up on EKS. First, you need to install the cluster autoscaler. It's an open source project, and it consists in a pod that will run on the cluster and interact with the cloud provider to request more nodes when there's no room left on the cluster for pending pods. Then you'll want to define the node labeling scheme so that you can select nodes with label selectors and assign, for instance, executor pods to spot nodes. So we show below how to do this. So we've defined a label Acme life cycle that conveys whether the node is a spot or on demand, and the label Acme instance with the instance type. Then to make the labeling scheme work for node pools that scale down to 0, you will need to manage node pools manually as autoscaling groups and add autoscaling group tags matching your node labels. This is shown below again. So the cluster autoscaler knows from the tags on the right that when a node from a given autoscaling group is launched, it will have the node labels on the left. Okay, so we're finally ready to use node pools with Spark, and in particular, spot instances for executor pods. So we show on this slide how to configure Spark to use the node pools that we just defined. When running Spark submits, you can add a global node selector for all Spark pods with this Spark config. This is slightly limited as the node selector will be applied to both driver and executors. Another option is to use pod templates, which have a richer API. If you're using the Spark operator, you can define node selectors in a style very similar to the Kubernetes API. Now a few words about dynamic allocation. So on Yarn, you can enable an external shuffle service and then safely enable dynamic allocation without the risk of losing shuffle files when downscaling. On Cube, the exact same architecture is not possible, but there's ongoing work to work around this limitation. In the meantime, a soft dynamic allocation is available in Spark 3.0. The Spark driver tracks the shuffle files and only allows to evict those executors that do not store active shuffle files. This works great in practice, though on average the scale down of a Spark application is a bit slower than on Yarn. It's a major cost saver on average on Cube. So now, when a Spark application requests a new executor, it takes a few seconds to create a new pod if there's room on the cluster. If there isn't room on the cluster will scale up, and it usually takes a minute or two to get a new node. So as a consequence, if you're willing to trade off some cost optimization for lower latency, you can reserve some extra resource in your Cube cluster with over provisioning. So the idea is to run some low priority pods that do nothing. They're called post pods. And when a Spark application is run, the post pods will be killed to make room for the Spark executors. And then the post pods will be scheduled again and cause the cluster to scale up again. So the interesting thing here is that the cluster scales up in the background thanks to the post pod, and not synchronously when a new executor pod is requested from the cloud provider. All right, next topic up is monitoring. So the first type of monitoring to set up is pod usage monitoring. So the Cube dashboard is an open source project that you can install and that reports CPU, memory, and disk usage in a web UI. The GKE console as well provides some metrics about all this. But the main issues with this type of monitoring is that first, it's hard to link with Spark phases like jobs, tasks, and stages. And the executor pods are removed once the Spark app is finished. And so you lose a lot of useful metadata about those metrics that you collected. So the other side of the coin, as I mentioned, is understanding what happens in a Spark application. And for this, you can rely on the Spark UI that every live Spark application exposes on port 4040. And you can open a local proxy to it with a port forward. But for the completed applications, you need to host a Spark history server, and this takes some work. To do this yourself, you should configure a Spark to write the Spark events logs to a persistent storage like S3, then install the Spark history server on Cube and configure it to read the logs from the persistent storage. This is the hard way, but as of next week, we're happy to offer an easier way. We have open sourced the Spark agent, which will stream the necessary metrics to our backend and give you access to the Spark UI hosted on our website. This is a free monitoring tool that will work from anywhere, from the cloud, from on-premise setups, on Kube or on Yarn, in EMR, and more platforms. So you can check out the links here to know more about all this. Just a few words about why we work on this project. Well, it's our first milestone to the release of replacements for the Spark UI that we call data mechanics delights. It's a monitoring tool that aims to make the Spark developer experience delightful, and it will let you visualize memory and CPU metrics just alongside your Spark jobs and tasks. This tool will be free and cross-platform, and we want to make a release in January, and we love your feedback on all this. And so check out our website if you want to learn more. Okay, so now that we've set up a high-performing, cost-efficient, and well-monitored cluster, we're going to walk through a full example of application development in the context of Spark on Kube. All right, so now it's the risky parts of the presentation. So let's see some code. Or maybe no, it's a mistake. Actually, I have a few more slides about what I will show first. Just a short introduction. So we'll use Docker to package our Spark application. So as Jay said, it's a great progress that was enabled by the use of Kube as a Spark scheduler. Since before Docker, you always had this fear that when you push your application to the cluster, it does not run as expected. Most of the problems came from dependency management. In Java and Scala, you needed to make sure that your jar dependencies have matching versions with the Spark distribution on your cluster. And on Kube, the Docker image includes the Spark distribution. So if your app runs locally, it will run on your production cluster, and you won't have any bad surprises here. In Python, you needed to package all your modules and third-party libraries in a zip file or in a wheel or in an egg, push this to HDFS or an object store, and refer to it in your Spark submit arguments. This was super brittle for non-pure Python libraries like NumPy, which uses C code in the background. Now everything is in the Docker image and matches the target operating system by design, if you will. And finally, Docker makes iteration cycles very short thanks to its smart layer caching. So we're going to show you an example of this workflow, and we'll run an image locally, then on a Kubernetes cluster, iterate a little bit on the code, and optimize performance at scale. We'll use an example from EKS, a company that was acquired by Spotify. The data set is 1 million songs with acoustic features attached to them, and we'll use those features to create harmonious playlists. So now is the right time. So let's have a look at some code. Okay, so here's a local folder with the code of my Spark application. So thanks to Docker, the projects can adopt a standard layout for a Python project. There's a requirements file with third-party dependencies inside. There is a custom module with a few functions I wrote to analyze and compare songs, and the main script where most of the code is. So it's a Spark application, of course, and we load songs from a data source. We compute some signatures for every song. We isolate the songs that we want to use as seeds for our playlists. We compare every seed song with every other song in the data set, and we keep the 10 most similar song for every seed song to form a playlist. And eventually we collect everything to the driver with the pandas and print the playlists to the driver log. The Docker file is fairly simple too. There's a base image. It's a Spark. It's a PySpark image that we offer, and it contains some connectors to the object stores of the major cloud providers. The Docker file installs the libraries from the requirements file, and it copies over the source files to the working directory. Okay, so let's build and run this image locally first. So here I'm building it, and it should go pretty fast, as it's not the first time I'm building it locally. Okay. So it seems to be a bit longer than I would expect. I think the cause might be Zoom. So now let's run it. And there's one interesting thing here to note is that I'm mounting the working directory as a volume into the Docker container, so that we don't need to rebuild the image every time we make a change to the source code. So the application is now live locally, and on the side, let's run it on a Kubernetes cluster. So let me run the command first and then explain. So the image is built again, and then the command will make a call to the REST API of the cluster to submit the Spark application. So we should see this in a few seconds. And okay, so it's now pushing the image. Okay, so the call should happen in a few seconds here, and the application will be live on the cluster, and we should see the live log stream. Okay, and I've wrapped the operations in a just file. So just is a replacement for make that's easier to work with, and the main command here is run cluster, and you can see here, so the call that's made to the REST API of the cluster, which is very similar to that of the Spark operator. Okay, so now let's move on to the cluster and have a look at the app running. So here I'm showing this in our product, but it's just a Kubernetes cluster with a few tools on top to make it easier to monitor. Okay, so it's a bit slow. I'm really sorry. It might be because of Zoom. So it's not as slick as I would expect it to be.
It happens to all of us.
Thank you.
If you want, for the moment, you can stop sharing your video. Sometimes that speeds up things if the demo gods are painful. I also have a long list of questions, which I'm sure people would love if we ask, if we have time. If there's any pause.
Yeah, it seems to be working now.
Great.
Cool. So we can see our app here that's running, but for the sake of this demo, I'll cheat a little bit and I'll pretend that the app is finished and that it has failed. So I'll show some runs that I made a few days ago. So here is the run that failed in my demo, and this run failed after about 20 minutes. So let's dig into this app, and we can see here, so the stack trace of the error, and what we can see is that we have some issues with the singular matrix in our data. So this is the life of the data engineer. Sorry, there are some issues that you just run into at scale, since you need to process enough data to encounter all the edge cases. So let's fix this into the code. So it's a stage error, so I know where to fix it. But let's do this, and let's build the image once more and have it running again. So here I'm just protecting this part of the code where some matrices are inverted, so that we don't have a problem with those singular matrices. So I'll run the app again. Okay, so the image is built again, and we should see our changes being sent to the Docker registry. Okay, so I would like to say that it took less than a minute to do all this, but I'm not sure, as it's a bit slower than expected. But yeah, it was pretty short all the same to have an app running, and then to see that there's a bug and change the code to have it running again. Okay, so let's go back to the cluster and pretend once more that the app is finished, and that this time it was a success. It was 50 minutes, and let's have a look at the results. So the driver logs have been rotated by a cube. So I'll fetch them from the archive, so that we can see the results. Okay.
Maybe I can just jump in and answer a couple of questions I've seen in Q&A.
Yeah, please.
I've seen two questions from Kailash. One is, so in this, how is it different from ephemeral clusters available on the cloud? And if I run a 200 executor job, then nodes will be created dynamically and destroyed once the job is done. Is it more like ephemeral? And how does it differentiate between Yarn and Kubernetes? So regarding differences between Yarn and Kubernetes, I'll send the link to a blog post that goes into more details. But so to answer more your question around scaling, okay, if you request 200 executors, chances are maybe there isn't enough room on the Kubernetes cluster. And so if you enable what we call cluster autoscaling, indeed, you will get new nodes on the Kubernetes cluster. And indeed, once the application is done and these nodes are not necessary, they'll be released back to the cloud provider. So in that respect, it is cost efficient like an ephemeral cluster. And that's a good thing. This being said, okay, ephemeral cluster is typically what we recommend on, I guess, Yarn setups to guarantee isolation between different applications. But here, the Kubernetes cluster can be shared across multiple apps. So if once your 200 executor application is finished, if there's another application that starts, it's going to be able to grab the capacity in just 10 seconds. So reallocating capacity inside the cluster is very fast. I guess that's one of the difference. I'll send a link with more details. Giving the floor back to you, Julian.
Okay, thank you, JY. And so here we can see the results. So we can see that we have some playlists that make sense to some extent, rock with rap, rock with rock, sorry, rap with rap, and classical music with classical music. Okay, so let's look at the performance now. So it took 50 minutes to run the app. So there might be something that we can do here. So let's head to the Spark UI, where we can see that there's one large job with one large stage inside, and more than 600 tasks in this stage. We can see that the tasks are a little bit skewed, but there's not much that we can do here as it's in the data. And we can see here that the time spent in task is actual compute. There's one thing that we can't know from the Spark UI is whether the application is IO bound or CPU bound. Here we use the 8 cores for each executor on a data mechanics cluster. This maps to an R5 2x large machine with 8 cores. So this instance type is actually actually has the same network throughputs as a R5X large, which has just 4 cores. So if the application is IO bound, an idea is to use smaller executors, but more of them. And so we'll pretend again that I run this, and we'll see that the performance is now much better. All right, so here we go. So now it took just 30 minutes to run the app. And so the only change was that we used 4 cores per executor and not 8. And what changed is that the time spent in tasks went from 73 hours to 39 hours only. So this shows that we were right and that the application was IO bound indeed. All right, so I hope it was interesting to you, this demo, and that it showed you the kind of dev workflow that is enabled by the use of Docker with Spark. I'll leave the floor now back to JY, who will talk about the future of Spark on Kubernetes.
Thanks a lot, Julian. Yeah, so I was just answering one more question on the Q&A. My last section is super short, so I think we will be able to answer more questions. I just want to talk for a couple minutes about the future works that are planned for Spark on Kubernetes. So yeah, next slide. We're going to see a timeline. So Spark on Kubernetes was released in February 2018 with Spark 2.3. It was pretty bare bone. In November 2018, Spark 2.4 came out and added many essential features like client mode, volume mounts, better dependency management. Then in June of this year, Spark 3.0 came out and added support for dynamic allocation through shuffle tracking. Julian explained that earlier. So next slide. Maybe we, yeah. Then in December, so next month, we're scheduled to release Spark 3.1. And in this release, we're going to remove the experimental label from the documentation. So we're going to deem that Spark on Kubernetes is production ready. And then there's another feature that I'm going to be talking about. Maybe next slide. So yeah, this is just the fact that it's going to be GA. So right now, if you look at the Spark doc, it says the scheduler is experimental. And so this sentence is going to be removed. Next slide. One actual feature that we're excited about is better handling for node shutdown. Okay, what does that mean? When a node is going away, whether because of a planned maintenance from the cloud provider or a Kubernetes reason or because of a spot kill, we're going to get a notice from Kubernetes or from the cloud provider. This node is going away, 30 seconds from now or a minute from now. And we're going to use this lapse of time to, next slide, to one, stop scheduling tasks on the executor who's going away, and two, copy, shuffle data to an executor who's going to stay alive. And this way, next slide, the Spark application can continue, almost unimpacted without losing the precious shuffle files. So this is something that will make Spark much more stable, in particular when you work with spot nodes, and that we're looking forward to. Next slide. And then another big improvement, which is still in the works, is to potentially use remote storage to persist shuffle files. We don't have a planned deadline for that, but I'll explain what this means. So next slide. Instead, today shuffle files are stored directly on the executor, and this would still happen. So first, the shuffle file is written locally synchronously, but then next slide is going to be copied asynchronously to a cloud storage like S3. And then next slide, we're going to see that on the reduce side, when we need to fetch the shuffle file, if the fetch fails because maybe the executor is gone, then next slide, we're going to get it from S3. And so again, this is a feature that will make Spark more resilient to node loss, and it will also enable dynamic allocation unconstrained. So we don't need to track where shuffle files are because we know they're stored on S3. Next slide, I believe. This is it, yeah. So thank you so much, for tuning in. I hope this was helpful. We've already answered some question in Q&A, but you can ask more. And I've also posted the link to the slides, and I think we'll post them on the meetup. This was one of the questions in the Q&A.
Yeah, absolutely. Thank you, JY and Julian. This is a great talk. This would be the time where we would give you a round of applause, but of course, we can't hear everybody in the panel. I think there was a lot of questions. We do have some time for some more questions. There was one that was asked early on, and I kind of skipped over it. So the question was from Kailash. How is this different from ephemeral clusters available on clouds? The question is, when you run Spark on Kubernetes, how is that different from ephemeral clusters on clouds?
Right. Yeah, I think most people, when they use Kubernetes, the Kubernetes cluster is not ephemeral. When we talk about ephemeral clusters, it's typically on a provider like Databricks or maybe EMR, where you just spin up a cluster, run your application, finish it, and you get the same indeed cost efficiency if you use Kubernetes and enable Kubernetes cluster auto-scaling.
Oh, I think we lost you, JY.
Then,
oh, there, you're back. Great.
Apologies. And so you're going to request executors, add new nodes to the Kubernetes cluster, and then once your application is gone, release the nodes back to the cloud provider. So in this sense, it's similar that you get the same cost efficiency. But on the other hand, there are more things that it's not fair to compare Spark and Kubernetes and ephemeral clusters, but yeah.
Yeah. Okay. Thanks. And then Loan has another question that has not been answered. How does structured streaming work on Kubernetes? So do you have one Spark UI for each structured streaming process? And how are the checkpoints stored in the streaming case?
Yes. Okay. It works similarly than on other Spark platforms. That's the good news with Kubernetes Spark and Kubernetes doesn't reinvent the core of Spark. So most people indeed would choose to run different Spark application as different Spark app, which each have their own Spark driver. And so one Spark driver means one Spark UI. So indeed, you have one Spark UI for each process. Where do we store the checkpoints? I think these would be stored in object store. Julian, do you have a more precision on that?
Yes, I don't think I can say more than that, but in the context of a kube, yes, you'll store the checkpoints on object stores so that you don't lose them as the cluster scales up and down, and there's not enough room in the memory and on the disk of your Spark driver.
But does that work for streaming? Because maybe there's some delay in getting the object from S3 or from your blob store.
We have not seen this, but I might be corrected.
Yeah. Okay, great, thanks. Another question from Aruna. Are you using open source enhancements for executor decommission? Is that something internal on your end, or do you have any plans to open source those?
Yeah, so this improvement that we presented will actually be part of Spark 3.1, so it'll be open source, absolutely. There is one thing that you need to do on the Kubernetes cluster to make it available, and you need to basically install, I think it's a daemon set that is going to warn, so that you're aware that the spot node is going away. It's in the slides. So yeah, under the hood, we didn't reinvent proprietary stuff. We just stick together a bunch of open source projects to make it easy.
Nice. And I think Aruna is also a fan of the enhanced Spark UI.
Great. Yeah, we're planning to open source it. So next week we're releasing the agent, which will be open source. So the agent will run inside your Spark application, and it will be streaming logs and metrics to our backend. And this is open source so that the community can audit, make sure we're not trying to, take confidential information from your Spark application. The backend part is pretty complex. So right now we're not thinking of open sourcing the backend. We're running a real-time log collection pipeline, and we're storing it in a time series database and so on. But maybe in the future we could open source that part too, based on the community feedback. Yeah,
it sounds very useful. I think we're all hitting limitations with like our own Spark UI, whether it's the Spark history server. There are too many applications, can't serve them all. So I think that's a really good improvement.
Yeah, there are so many pain points. It's so broken in some way. On the other hand, it's it's still the main tool that does the job for most people. And what I want to say is, even though the backend is not open source, we do want to make it free and cross-platform. So we want to make it such that you could use Delight on top of EMR or Databricks or your own on-premise setup or your Spark on Kubernetes open source setup, etc.
Nice. That sounds really useful. I know we're getting close to 1 o'clock, so I think the questions that have been asked in the Q&A have been answered.
I have a question.
Oh, yeah.
So have you looked at the Apple's open source work on the Prometheus? Hope I pronounced it right. So these are monitoring framework.
Prometheus.
Prometheus, yes, exactly. So on the Kubernetes, and I think they talked on the June's Spark Summit.
Do you refer to the work of Luca Canali to have like a graph and a dashboard with the metrics about the pods and the stages and everything.
It's a bunch of monitoring specifically for Spark, I think, and that's the author DB Chai and the other guy on the core Spark infrastructure team at Apple.
Okay, so no, I don't think that we've seen it. Do you?
Always on a Spark,
yeah.
Spark Summit in the June talks.
Okay, great. Yeah, it'd be great to watch it.
Anybody who's interested in Prometheus sending metrics to Grafana, you should also look into Thanos, because if you have multiple clusters, you can aggregate all the metrics into Thanos. So you have a single window. Very handy. Great. This has been a great talk, and I think all of our members have really benefited. So I see that we'll be posting the slides on our meetup page. We'll be posting the video on our YouTube channel. And I guess I just want to thank our speakers from Data Mechanics. This has been a great talk. And thanks to AI Camp, also a huge partner in this. For those of our members, I want to remind you that next time, our next meetup is we have a talk from Facebook. So come and hear Paul Tanaka, who's a software engineer from Facebook on the data classification team. So that'll be our next meetup. Lots of great talks. Thanks so much. And I'm sure we'll be pinging you in case there's any more questions.
Thank you, Anya, for hosting us, and thanks everyone.